Okay, welcome to my seminar, Building a Graphics Converter from the Scratch. As you see, this is not a seminar about coding, this is a seminar about the aesthetics. When I say welcome, I mean welcome all your graphicians. How dare you to build up a graphics converter when you know pixeling is the only stuff. But we see what we can do for you. Graphics converting is done by transferring RGB graphics into old PAL graphics for the Commodore 64, for example. What we see here is the analyzed spectrum of RGB graphics. We have gray tones, which make the luminance. We come to this later. We got several colors illuminated from black to white, and we got the colors themselves. We see here on the upper side the pure colors, and on the down they are shaded. It's the RGB graphics model. It's nothing special indeed. But when we come to the C64, and its possibilities, we have the same idea, the same spectrum, but a totally different view. We have quite a bright spectrum on luminance, but when it comes to color, it's all crunched and squeezed. And as we see here, the spectrum dithers up. So we cannot convert graphics that are too dark or too colorful. And on the PAL system we have 17.7 million colors. I don't tell you any new things here. We have full saturation and we have a full range of luminance, which means we have 3 color channels, and we can give them values from 0 to 225. On the C64 we have only 166 colors. We have the PAL saturation, which means we have only 75% of luminance for the PAL colors. We have full luminance on gray colors, but we only have 75% of illumination and saturation for the colors. And we have, as I told before, visible dithering. Yes?
Is the PAL white much whiter than RGB white? At least that's what I heard.
The white is not exactly the same as the RGB white, because the PAL color system is squeezed itself. When you are displaying PAL, you don't have values from when you convert PAL to RGB. We don't have colors from 0 to 225. We have colors or values from 16 to 235. That is because the creators of the PAL system wanted to have an overhead on the lower and upper spectrum.
So that means that you cannot describe all color colors in RGB because white can be much brighter.
The opposite. You can't display on a PAL system. You can't display all RGB colors.
And you can display the full color range in RGB.
Yes, because the PAL range is squeezed, not the RGB range. It's the PAL range that's squeezed to colors 16 to values 16 to 235. Okay, so we go on here. I converted the color bars to a grayscale image, and we see here that white and black are quite strong in their appearance, but the colors are not as bright as the extremes. So in fact, the colors can become values from 16 to 176. That means if we go back, we see at the upper bars we have a spectrum. No, we have a saturation of 75%. That's what I meant at the beginning. We have how you convert graphics. There are many ways. Lots of people in the old days did plane conversions without dithering. And just a moment. Some people do noise dithering. Some people do audit dithering. Both features have pros and cons. By noise dithering, we have a very nice grade of shading at the black and white tones, at the gray tones, but the colors are quite crappy. At the audit dithering, we have a clear overall appearance at colors, as we see at the last square down here. It's yes.
I have just a question.
Yes.
Concerning the previous part, and how did you measure the difference between the 64 colors and the RGB system?
Well, I didn't measure them. It's some kind of electronic thing. If you look up at old electronic books for media creation, for example, you get those values. What you could do if you want to measure them yourselves is capture them. Capture them from a test image from the color bars. The color bars come out of every camera. Capture them with your capture card on PC and measure them. You will find exactly those values. It's no secret.
So they are documented, so to speak.
They are documented.
Thank you.
Oh, that was the wrong one. Oh yeah, black and white. Black and white are my most favorite topic to talk about, because what we see here is at first a full converted picture in black and white. What we see here is frame 1 and frame 2 of the pictures, as I used interlace. The interlace is swapping 2 frames at an enormous speed of 50 Hertz. And what makes this picture interesting is that you cannot, or you may not only use the original gray tones of your C64, but you may use colors to interpret gray tones. For all you people who don't know what I'm talking about, this is a color circle. And one of the general rules of this color circle is that when you take 2 opposite colors, for example, violet and yellow, they erase. If you layer them, the color erases and becomes gray. Same works with cyan and orange, for example, or red and green. So if you go back here, we have all those colors that make the gray tones. That gives us opportunity to enhance the gray spectrum and to enhance the visual effect. There. Various graphics format on the C64. I took a nice picture from Boris Vallejo, which has who has quite a history on graphics in the C64 scene. You find various pictures of him in various demos. And I take it in order to visualize some graphics formats. For example, we have here the plain high-res graphics format. Plain high-res is 220 times 200 pixels, and separated in blocks called characters of 8 times 8 matrices. Per matrix we have 2 colors. I don't tell anything new here. How High-res is very blocky, as we see here. Wrong button again. But the other native graphic format is multicolor. We have more colors here, but we see that the pixels are stretched in X. We have the high-res FLI, which is an enhancement. We don't have matrices 8x8 big, but 8x1. So we can change, or we can choose between two colors in a matrix of 8x1 pixels wide. The same is multicolor FLI. We have several restrictions here, but it comes closer to the original. What we will talk about today is the ILM format. As you see here, it's pretty enhanced and has an overall exacter appearance in comparison to the original. What is ILM? ILM is a quite new graphics format for the C64. We can change background color in every raster line. So the DO21 color is changed every line, and we can do that for graphics enhancements. We have X shiftings every raster line up to 7 pixels, which means we can take a high-res graphic and shift every line up to 7 pixels, and therefore get rid of the strong restrictions of the matrices. We have, no, wrong button again, damn it. We have color RAM interlace. The C64 has a color RAM. It's a matrix of 40 times 25 colors, which give a background color to every high-res matrix. We can select the graphics mode, high-res or multicolor, in every raster line. So we can mix the graphics modes. So it's a pretty advanced thing, and the best of it, it's pure bitmap. No sprites used in here. So we don't mess up with the memory, and we have a quite easy to use system. When you convert a graphic like this and use, for example, the ILM, of course you may invent your own graphic system. That's what it's all about. That's why you're sitting here. But when we use the ILM, we have to convert the most restricted parts first. Of course, we could go and say, yeah, we have an ILM, an FLI image, and we can put all the colors and convert all the colors and see what we can do with them and fill the gaps with additional features. No. The opposite way is the best one. We first look what we can do with our features, what can our features cover in the conversion, and then go to the usual FLI, multicolor, high-res, whatever mode to fill the gaps. You're more flexible. So what we see here is simply a changed background color for every raster line. Of course, this thing is interlaced, so you will always see a display for frame 1, frame 2, and a merge. What we see here is more interesting because it's the color RAM, and the color RAM is X-shifted, I mentioned before, is X-shifted. So we don't have the pure color RAM, but we have shifts in here. The shifts aren't the same for both frames, of course, and it's quite wonderful that we have actually 2 frames, because no one ever before did interlace the color RAM for full screen graphics. I don't understand why, because you have, when we have the C64 screen, we have the border, and there's enough time to interlace the whole color RAM on the border with speed code, but you get nice effects. You get further effects if you shift the different frames by Y. So the colors overlap. We can work with that. But the most interesting feature actually is the shifting, because you can you can use a proper visual appearance here. As I said before, we fill the gaps with. Actually, this is the video RAM added, and I used it to fill the gaps exactly. So we have here the final picture in FLE multicolor plus those features, and what we do next is when we build up a converter, we should look where the mistakes or where the pixel is that can't be covered by our conversion routine. I marked them red. So you see there are several complex areas that can't be covered by standard converting, by setting up palettes, and there is too much information in those red areas. When you have a matrix of 8 times 1 or 8 times 4 colors in multicolor, you can you can use a restricted palette, and that palette cannot cover the whole thing. So we have to substitute those information. We have to substitute the information. And we have to substitute by the best matching color. So how do we do that? We compare the luminance. For example, if we have a pixel or a matrix which has a brown pixel and a yellow pixel, and we have a pixel in between that doesn't match to those two colors, we have to look, for example, it's a red pixel in between. We have to look, is the luminance of the red pixel more to the brown or more to the yellow pixel? We would decide it's more to the brown, but we have to automate this and make it part of our conversion routine. So, yeah, we have the error mode and the substituted class. So the human eye isn't very capable of dividing colors themselves. So if you substitute by luminance, the eye gets tricked, and it's absolutely okay for the appearance of a graphic when you substitute by luminance. So we, again, have the original RGB image and a thing what I call a raw 136 image. It's a plain conversions without any restrictions. We have the high-res mode, we have every possible color. I convert my graphics usually to this basic kind of image. In order to get the color, in order to get the resolution, and in order to look what it could be, what my conversion routine could or should look like. So at the end, we have the ILM multicolor conversion. And when we compare, of course, we here have high-res and here multicolor. We have quite nice conversion result, I think. In order to check out how good our conversion is, we can use Photoshop's difference filters. So we can overlay those two graphics and check the differences. And I marked them gray here, and I think it's proper. All the light areas are big bugs, but the darker the color, the better the result is. So we get a method here to measure our work. Yeah, that's a close-up. For the face, the human eye, usually when a person is in an image usually looks at the face, and we have to check here, is the face okay? Which actually is. So, I told you something about interlace and about multicolor. Now we come to high-res. When you use interlace, you actually have to convert two pictures. Of course, because those two pictures are displayed after each other. Those two pictures will, when you divide colors, will possibly look very different in their color appearance. And as you see here, it's a good example for flickering hell. As we see here, we have much of white areas, and we have dark colors here. So what happens when we go to interlace modes? It will flicker like hell. How can we avoid this? It is quite simple. The answer is we have to do scanline swapping. You take a scan line of each picture, every raster line. So scanline 1 is from picture 1, scanline 2 from picture 2, and so on. Reduces flickering to the max. But we have the result here in our old release. Actually, the first image, also in Boris Vallejo image, they're quite colorful, and use them when you write on converters. They are wonderful. But flicker reduction, flicker reduction can also be done by selecting the colors in a proper way. First of all, we have to check what color room we open in order to get a palette. What I have done is separated the original RGB color to luminance and hue, the color angle, and made a C64 color field. I plotted, if this is the color angel and this is the luminance, I plotted the C64 colors and gave every color enough room to expand until it hit another color. And if we do conversions, we can use this color room for RGB colors. We can take a pixel of the original image, can find the Y and the H component, and can do what I call real-time table access. So we can look if a pixel is green, doesn't matter which green, we can access this table and see, yeah, it's green. Doesn't make more sense because we don't have to calculate any color, which takes times and times and times. Of course, we have the same color room for interlace. So we have the possibility to actually get a pixel and get the proper color and determine it even more. For all you freaks out there who do dithering, we can even go more in detail. And what we see here is there are large black and white areas. And these areas are due to the pulsing, though. We determined at a previous time that we have a problem to display the PAL signal proper, and that results in a large black and a large white area. Our colors are squeezed to the middle of the luminance spectrum. So basically, we get the aesthetics of conversions, and I hope you have any idea or any inspiration got how to build up a routine and what kind of things you should think of. Last thing is when we talk about graphics, we don't have to talk about big graphics. We have to talk about any new challenge on an old machine. What we see here is actually a graphics on, or our graphics on the lower border of the C64, a restricted area which was told of that graphics are never possible. So when we convert graphics, we should use a new challenge and should write a converter which converts graphics for special areas or special restrictions, and that's the fun part. In other ways, a new converter wouldn't make sense in any way, because there are plenty of good converters out there. So, for example, we take the challenge on graphics on border. What we see here is multicolor and high-res. You see the high-res modes are not quite good, but when we talk about multicolor, we can talk about graphics, and here are a few examples of massive restrictions which can be illustrated by a good conversion routine. So have fun and make good conversions. Don't forget to pixel your graphics to add a nice logo, because converting photos is quite boring and doesn't take anybody nowhere. And you see, good photos are possible on C64, but who cares? It's your work that matters. It's your talent, your ideas, your inspiration that makes good graphics. That only can be the beginning, and I hope you will have fun, and I hope you get some ideas. That's it. We now may have questions. Are there any questions about the whole topic? Anything you may ask? Yes.
Do you think it would make sense to analyze the original graphic on different, how to say, scales, so to speak? So you don't start with the original graphic and try it to convert it somehow, but you first pre-process it.
Yes.
And maybe get 3 different versions on different scales where different things are filtered out.
Mm-hmm.
And then combine the result to get some optimum?
Well, actually, when you check your motives, you should, or when you develop a graphic that you want to convert later on, you should think of some background, some middle, and some foreground, for example, and maybe you convert all those 3 parts separately and merge them on your target system. That would be possible. Or you merge them on PC and have to give them several different colors or several different color themes. For example, when we have a background could match in the blue and purple area, whilst the foreground could be here and could be yellow, and therefore on rules of art would make a perfect contrast. So when we search for the motive of a graphic, we always have to choose carefully what we convert, what we work on.
Do you think it could be possible to automatize this procedure?
Well, automatizing creativity is quite...
I would not go that far, but...
a difficult topic. Well, no. Yes and no. It's quite hard to tell a computer to separate, or to let a computer separate what's background and what's foreground. You as a painter, you know. But for the computer, it's all areas, it's all the same. So quite hard.
But you could do like context-aware stuff, or?
Yes.
You could do like context-aware stuff, like find edges and then maybe some like avoid dithering along the edges.
Yes.
Something.
Okay, of course you can, which would be quite sensible in the face area, for example. We have a low contrast area outside the face, and we could write a piece of software which detects the contrast and the luminance fields, and on maximum swappings we could tell the routines that another area or that a area swap has happened. We could do this, yes. It's lots of work. For example, we could do this on the sky and on the face, but we would have a problem on the rocks hanging down. The computer wouldn't know that this is some kind of background and would detect it as a foreground, possibly. So we would get problems there. Okay. No, okay. Any questions? Okay. Then, thank you very much. Thanks for attending the seminar. See you next time.